Bismillahirrahmanirrahim. Our topic today is the axisymmetric element. It is very extensively used in solids of revolution that are subjected to axisymmetric loading. There are many examples, most notably rotating solids. Because when a solid rotates, it is subjected to centrifugal forces. Also, a very common one, pressurized pipes, etc. Now, this solid of revolution is shown in the figure. It will be subjected to body forces and pressures. The most common type of body force would be something like this. Body force in the z direction. Predominantly, this will take the form of body weight. Let's specify the coordinates. This is the r direction, this is the z direction, and this is a convention. You have r and z coordinates because this element, axisymmetric element, is a 2D element. And if the conditions of loading and geometry are satisfied, that is, it's a solid of revolution and the loading is also axisymmetric, then you are only required to model this using this one plane. One plane is enough. Obviously, you will subdivide it. You will subdivide the plane. You will, for example, if you are using axisymmetric, if you are using simplex elements, you will do this kind of meshing. So you have here as well, but this one plane is enough. So you are only requiring basically two coordinates, r and z. R is the radial direction, z is the axial direction. Now, other body force, which is very common, will be applied because of centrifugal force. And this will be if this revolves, then it will be in this direction. And obviously, this is not to say that is in positive r direction, it is in every direction, because all these, the shaded plane shown, any plane of this body subjected to this kind of loading is experiencing exactly the same thing. Now, when it comes to pressures, there would be a pressure in the radial direction. Similarly, if you think this pipe is subjected to internal pressure, then this will be PR. Obviously, on all planes this is happening, but we are focusing just on one plane. And if there is another pressure in the longitudinal direction, for example, this would take negative sign, obviously it is downwards, but this will be PZ. So we need to incorporate all these body forces and pressure forces in our formulation. Now, if we take one of these elements that make up this axisymmetric plane, and using simplex elements, we'll have for any simplex element we have three nodes I, J, and K, because recall that this is a 2D problem. Now, each node has 2 degrees of freedom. And again, by convention, this is called UI, this is not VI but WI, because it is in the longitudinal direction, so we call it W. Similarly, UJ, WJ, UK, WP. And again, we call that this is our R coordinate, and this is our z coordinate. Now let's recall the 2D elements that we have already studied. For plane stress and plane strain elements, the interpolation function was similarly. We have this same for V also. Now in this case you have the same thing essentially, but with adjustments made for the difference in the coordinate axes. Now in this case, recall that the shape function expression, the generic expression was where beta took the form I, j and k. In this case, axisymmetric, it will take the same form exactly, again with the adjustments made for the coordinate axes. That's all. Similarly, beta takes the form I, j and k. Now the strains in the case of plane stress, plane strain problems, the in-plane strain components, that is, were epsilon x, epsilon y and gamma xy. Now in this case, axisymmetric, there is one more strain component, but before coming to that, the three strain components are quite parallel. In place of epsilon x, we have epsilon r, radial direction, only the coordinate axis has changed. In place of epsilon y, we have epsilon z, and in place of gamma xy, we have gamma rz. So these three are just affected by change of the name of the coordinate axis. That's all. So this is called the radial strain. The longitudinal strain, and the shear strain. But there's one more component of strain that is new for this element that didn't exist in the plane stress or plane strain situations, and let's see what that is. Looking from the top, we have this inner diameter, and you have outer diameter, and it goes on around 360 degrees. Now let's say that after deformation, that is after the application of the pressures and the body forces, let's say that this expands, the inner as well as they expand, and this the boundaries in blue, they show the final position of the inner and the outer diameter. This is an axisymmetric situation. So any plane, for example, take this plane, after deformation it must be the same plane, it will remain the same plane. No particle on this plane moves in the circumferential diagram. It cannot move because this is an axisymmetric problem. Similarly, if we take another plane, this one, any plane, we're talking about just any plane. If this was another plane, and after deformation it will still, so all the atoms, all the particles here on this plane, they will obviously move in the radial direction, but they cannot move in the circumferential direction. The circumferential direction being this one. So what happens finally is this. If we take this just as an example, these two planes that we have seen, and the new position of these planes is, and after deformation they become this, the blue in the final configuration and black being the initial configuration. Now take 2 points at a radius r from the center, from the origin. Now let's trace the origin by extending the two planes. This is point O and this is the center. Now the 2 points at radius r are shown. Now the same 2 points after deformation take this position in green now. So what happens is that a displacement u, which is the radial displacement, has occurred, and the same 2 points now occupy the position shown in green. Now if we call this angle as delta theta, theta being the circumferential coordinate, this is the circumferential direction. Now the arc length, the length of the arc in red before deformation is r delta theta. This arc is circumferential. Now the same 2 points now occupy the position shown in green. So when that happens, this arc length becomes then r plus u delta theta. So the point to understand here is that because the particles of any two planes, they must remain on the same plane, on their respective planes. So if a point moves in the radial direction, like we saw 2 points in red and occupied the position shown in green, then this necessarily produces an extension in these arcs, and that extension, because it is in the circumferential direction, that causes the strain epsilon theta, that is circumferential strain. And that epsilon theta can easily be calculated. We know the original length and the final length. The new length is r plus u delta theta minus the original length r delta theta and divided by the original length. This is the formula for strain, which becomes r delta theta plus u delta theta minus r delta theta over r delta theta, and this leaves us with u over r. This is a very peculiar expression because we are used to strain values that are differentials. This doesn't include a differential. This is simply the u displacement over the radius. So we are now obliged to add another strain component here, theta, and this is called the circumferential or loop strain, and the value is simply u over r. This radial strain value, in this case it will be delta u over delta r, only we have changed the coordinate. Here it will be delta w over delta z, again a change of coordinates and the displacement component only. Shear strain will be delta u over delta z plus delta w over delta x. Again, change of coordinate axis and the name of the displacement. The vector in our progression is epsilon is always linked by the matrix B with the nodal displacements. Now we know the epsilon vector, epsilon r, epsilon theta, epsilon z, gamma rz. They will be linked with this B matrix, which we come to presently, and then there will be the displacement, nodal displacement ui wi, uj wj, uk wk. These are the 6 displacement components we have already seen. Now recall that epsilon r, epsilon z, and gamma rz, they are exactly the same as before, with minor changes in the coordinate directions. So we can use the knowledge we already have, and so they will be nothing but bi0, bj0, bk0, the very familiar expression for you, and then you have we leave the space open for epsilon theta. Epsilon z will be the same, 0 ci, 0 cj, 0 ck, and here you will have ci, bi cj, bj, ck, bk. That leaves us with epsilon theta. Now we know that epsilon theta is equal to u over r, and u is nothing but ni, nj, nk, ui, uj, uk. Now epsilon theta will then be ni over r, nj over r, nk over r, and then we'll have ui, uj, uk. If that is the case, in the B matrix, we have to put in ni over r, nj over r, and nk over r at the appropriate places. The appropriate places being the first, third, and the fifth. But there's one more complication, and that is, for convenience sake, we have 1 over 2a outside. But in this expression, there is no 1 over 2a. So if we are going to put in ni over r, we have to include the effect of 2a also, so that it gets cancelled. So basically, 2a ni over r 0, because this has nothing to do with the w component. 2a nj over r, again 0. 2a nk over r, and 0. Now this is our B matrix. Now B matrix is a function of the coordinates r and z. This is again something unfamiliar for us. The first, third, and the fourth row, they are constants like before. But the second row is something new. That is, B is a function of coordinates r and z. R is visible in the expression itself. As far as z is concerned, focus on ni, nj, nk. You have to calculate ni, nj, and nk, which are functions of r as well as z. We'll return to this point presently. Once we have reached the stage of strains, then the next step, like always, is that of stresses. Stresses are and strains are linked by the D matrix, and in this case the stresses to mirror these strains will be sigma r, sigma theta, sigma z, and tau rz. The D matrix takes the form 1 plus mu, 1 minus 2 mu, 1 minus mu, mu 1 minus 2 mu over 2. Here we have mu 0 0 0 0 and this is the D matrix, and this time on the right hand side you have the strain vector. Once you have B in place, you can calculate strains, and from strains you can, using this last expression, you can calculate the stress vector. But you cannot calculate strains unless you have all the displacement values for all the elements calculated. And for that, obviously, you need to first be able to find the different matrices and vectors for the problem. And we take them up one by one. First of all, the stiffness matrix K. That is a very familiar expression for you. We always start from this expression. V E D D is a volume integral. Now B is a function of R and Z. In the simplex elements that we have been considering so far, we have been able to take this B out of the integral sign because it was all constants in there. But now we have epsilon theta, which is function of R and Z. So the solution here is we calculate B at R and Z, that is the centroidal values, and then this becomes B at the centroid. If that is the case, this is an approximation, but it does not give us large errors as long as we are careful in our modeling. That is, we have to be careful about the element size. If we do that, then there's nothing to worry about this approximation. So what happens because of this approximation is that we can write this K as, again, you can take this out. D is already constant, so there's nothing to worry about here. And this becomes this, and we can further write it like this. We can convert the volume integral into an area integral by using two pi r the circumference formula, and again R is the centroidal value of the radius. If that is the case, this is an area integral, then this gives us the value for the stiffness matrix. If we have B matrix calculated, there's nothing difficult about it. The next item is the force vector as a result of temperature change. Again, we start from the generic formula. This is valid for 1D, 2D, 3D, every kind of problem. And recall that epsilon naught was itself a vector. Using the same vector, the only difference being an additional 1 is there because of the addition of the circumferential strain. So if we put in these values, and again using the calculation of B at the centroid, then we can take this out. D is already constants. Alpha delta T, this is again these are also constants, and this again becomes volume integral. And again, using the same approach as we did last time, we can replace this by this expression. So this becomes Now recall that the D matrix is E over 1 plus nu, 1 minus 2 nu, 1 minus nu, 1 minus nu, 1 minus nu, 1 minus 2 nu over 2 nu 0 0 0 0 0 0. Now if we multiply this D, which is right here, with this 1 1 1 0 vector, we get E over 1 plus nu, 1 minus 2 nu, 1 minus nu plus nu plus nu, nu plus 1 minus nu plus nu, nu plus nu plus 1 minus nu, and 0. Now this is the product of these two. Now the other quantities, they are there too. Now we can make further simplification. This plus p plus nu minus nu, they get cancelled. So you have 1 plus nu everywhere here except this 0, and 1 plus nu is here also, so this also gets cancelled. So in the end you are left with, if you simplify this, this is also epsilon. If we simplify this, we are left with E alpha delta T B transpose over 1 minus 2 nu one 0 2 pi r. This is the expression for F naught. Any question where you have temperature changes, then the force vector because of those temperature changes will be calculated like this. Again, very simple. Once you have B matrix, the other values are very simple. Material values, material constants, A and R come from the geometry. Again, R is the centroidal value. When we talk about centroidal value, here Ri plus Rj plus Rk over 3. Similarly, when we were calculating the B matrix, the Z value was, centroidal value was Zi plus Zj plus Zk over 3. And R again, Ri plus Rj plus Rk over 3. Now the next vector to be calculated is the body force vector. Body force vector again will be starting with the usual expression and transpose Z. These are the body force components in the radial and the axial direction. Now that this R can only be applied due to rotation, centrifugal force. This Z, this can be applied because of gravity, etc., or magnetic force or whatever. Now this FP can be calculated precisely. We don't have to resort to calculation at the centroidal values. We can use natural coordinates to our advantage here. So let's first recast it in another form. We can convert it into an area integral by again using the expression 2 pi r dA, but here r is not r in the centroid, it is a general r. Now this can be rewritten as 2 pi, take outside, and we use the product of r and the contents of the N matrix, Rni, Rni, Rnj, R and J, R and K, R and K. We have zeros here, and then we have R and Z, and then the DA. This is area integral. Now recall two things. R can be written using the natural coordinates L1 Ri plus L2 Rj plus L3 Rk. Also recall that Ni is equal to L1, Nj is equal to L2, Nk is equal to L3. If you recall these three things and put them here, then this expression for Fp becomes L1 square Ri plus L1 L2 Rj plus L1 L3 Rk R. Similarly, L1 square Ri plus L1 L2 Rj, L1 L3 Rk Z. Then L2 L1 Ri plus L2 square Rj plus L2 L3 Rk. This is R. Similarly, L2 L1 Ri L2 square Rj plus L2 L3 Rk. And finally, L3 L1 Ri plus L3 L2 Rj plus L3 square Rk R. L3 L1 Ri plus L3 L2 Rj plus L3 square Rk, and we have this dA here. Now there's one more step to go, that is the calculation of these integrals. Now recall that area integral formula, the factorial formula L1 alpha L2 beta L3 gamma dA was alpha factorial beta factorial gamma factorial over alpha plus beta plus gamma plus 2 factorial into 2a. We have basically two combinations. First one is Li square and Lj0 Lk0, which is 2 factorial 0 factorial 0 factorial over 2 plus 0 plus 0 plus 2 into 2a, 2 over 4 into 3 into 2, 2a. This is a over 6. The other, this is area factorial dA here. The other combination is, the other thing to calculate is Li power 1 and Lj power 1 and Lk power 0. Because it doesn't matter which of these has a power 1 or 0 as long as you have the same power. So this one is 1 factorial 0 factorial over 1 plus 1 plus 0 plus 2 factorial into 2a. This is 1 over 4 into 3 into 2 into 2a, and this is a over 12. So we can simply replace these values and get the final expression for Fp, which is 2Ri plus Rj plus Rk R, 2Ri plus Rj plus Rk Z. Next two will be Ri plus 2 Rj plus Rk R, Ri plus 2 Rj plus Rk Z, and finally Ri plus Rj plus 2Rk, R and Ri plus Rj plus 2Rk Z. This one is the result of, and on the outside you have pi a over 6. So this is your expression for the calculation of body forces if they are applied on your system. Now note that the body forces are not distributed equally among the 3 nodes. Whichever is located farthest away from the origin, that will get the maximum value of the force. Indeed, that should be the case because there is more material at the outside than there is at the inside. So more force should be applied at the node which is farthest away from the center line. Now the final expression to be calculated is that of pressure force, Fp. Again, starting from the usual generic expression, now we can again convert this into a line integral. Now this is a line integral, and let's say that the line involved is the ij line. Let me explain here. If this is your center and this is your body, then let's say this is the element I node, j node and k node. Now obviously this pressure, right, is not on a line, but it is basically on a whole area around 360. But we can convert this area into, using this 2 pi r formula, into a line integral. And what happens is like this. This is p, then if this is the p direction, then we can convert this into pr and pz. And in this case, this line shown in red, this line is hij, because the k element, the k node, though part of this element, has nothing to do with pressure force because it is interior to the surface. One more consequence of this k having nothing to do with pressure force is this. Using this r value and this, opening this up, product of r and n values, we get rni, rni, rnj, rnj. And then we have 0. These last two, they are associated with node k, which has nothing to do here, as long as the pressure is applied at the ij node. Now here we have pr, pz, 2 pi goes outside, and this is a line integral. Again, recalling two things. R is equal to L1 Ri plus L2 Rj. In this case, there is no k, and Ni is equal to L1 and J is equal to L2. If we put in these values in this expression on the left, then we get 2 pi is outside, then we have the integral hij, and what we get is this L1 square Ri plus L1 L2 Rj to PR. Again, we didn't resort to using r at the centroid, and hence this calculation will be precise. L1 square Ri plus L1 L2 Rj Pz, L2 L1 Ri plus L2 square Rj Pr, L2 L1 Ri plus L2 square Rj Pz 0 0, and you have then dh here. Now we have to again calculate these integrals. Now we have two combinations. One is Li square Lj 0, which is simply 2 factorial 0 factorial 2 plus 0 plus 1 factorial into h, which is 2 over 3 into 2 h, which is h over 3. The next one is Li power 1 and Lj power 1 dh. This is 1 factorial over 2 plus 0 plus 1 factorial into h, 1 over 3 into 2 h over 6. So just replacing these values, we get Fp 2Ri plus Rj Pr, 2Ri plus Rj Pz, Ri plus 2Rj Pr, Ri plus 2Rj Pz 0 and 0. This is on the outside we have pi h ij over 3. Now this hij obviously will be replaced by jk or ik depending on which two nodes are relevant to the pressure, and in that case the position of the zeros will also change. The first two points correspond to I node, then the j node and the k node. Here the k node is irrelevant, so we are using zeros here. Again, for this expression, note that it doesn't give uniform nodal values of pressure as a result of pressure to all nodes. The further away a node is from the center, the greater the share of force given to it, and obviously it makes sense because there's more area, more exposed area the further you go away in these systems. So this makes sense. There's one situation, however, where Ri and Rj are the same. That is, you're talking about an element side that is vertical. If it's vertical, then Ri and Rj are the same. If that is the case, that is, if Ri is equal to Rj is equal to R, this is encountered a lot, and in this special case the expression become, because this 2 Ri and Rj they become 3 R, so this expression then gets further simplified, and then it becomes simply this. Thank you very much.